Hello everyone, I am Dr. S. Jyoti, Assistant Professor in Physics at Fatima College. Welcome to this e-content module on satellite orbital patterns. In this video, we will understand what is an orbit is, and then we will classify orbits in two main ways: by altitude, LEO, MEO, and GEO, and by functionality, it including geostationary, polar, sun-synchronous, and highly eccentric orbits. By the end, you should be able to identify which orbit is suitable for imaging, communication, navigation, and weather monitoring. First, what exactly is an orbit? An orbit is a curved, regular, repeating path of an object around a space body, like a satellite around Earth. The object can be natural, such as the moon, or artificial, like communication satellites. Now, an important point: satellites don't stay up because there is no gravity. Gravity is very much present. They remain in orbit because they have the rigid right tangential speed. So gravity keeps bending their path into a curve instead of pulling them straight down. So we classify orbits in two practical ways. One by altitude, how high above the Earth satellite is. That gives us low Earth orbit, medium Earth orbit, and high Earth orbit. Two, by functionality, meaning the orbit's geometry and purpose. That includes geostationary, polar, and sun synchronous orbits, among others. So let us start with altitude based classification because it sets the foundation. By altitude, we have LEO, roughly from 160 km to about 1000 km in this slide, and commonly considered up to 2000 km. These slides move fast, completing an orbit in roughly 88 to 127 minutes or about 90 minutes. MEO from around 2000 km up to about 35,780 km with orbital periods from about 2 to 24 hours. And HEO, where an important special case is geosynchronous altitude, about 35,786 km, where the satellite's orbital period matches Earth rotation. Now let's focus on low Earth orbit. LEO is typically below 2000 km. A key advantage of LEO is high resolution imaging because the satellite is closer to the Earth's surface. It's also the region where human spaceflight commonly happens. For example, the International Space Station. A typical LEO satellite completes an orbit in around 90 minutes. The applications include Earth observation and imaging, remote sensing, and some telecommunication constellations and scientific missions. So, in the slide, examples include the ISS and the constellations like OneWeb. An ISRO example mentioned is a resort to be used for disaster management and monitoring. Next one, next is medium Earth orbit or MEO. This region sits between LEO and GEO, and it's extremely important for navigation systems. Why? Because MEO offers a strong balance. Satellites can cover a large area compared to LEO and still provide accurate timing and positioning. So this slide notes examples of navigation constellations. GLONASS operates around 19,100 km, while Galileo is around 23,222 km. So when you use GPS like services, navigation, mapping, location tracking, the satellites enabling that are commonly in MEO. Next, now let us discuss high Earth orbit, particularly the most famous type geosynchronous and geostationary orbits. A geosynchronous orbit means the satellite's orbital period matches Earth rotation, about 23 hours, 56 minutes, and 4 seconds. That is the sidereal day. A geostationary orbit or GEO is a special case of geosynchronous orbit where the satellite is also directly above the equator and moves in the same directions as Earth rotation. So, because of this, it appears stationary over a fixed longitude. This is extremely useful for telecommunication and weather satellites. Ground antennas can remain fixed continuously pointing to the same satellites. An important coverage is the three geo satellites evenly spaced can provide near global coverage. So this slide also mentions India's GSAT series as examples. So in this video clip, notice the difference between the geosynchronous orbit and geostationary orbit. If you measure the height of these orbits from the Earth's surface, both geosynchronous orbit and geostationary orbit are located at approximately 36,000 kilometers above the Earth's surface. A geostationary orbit is an orbit that lies directly above the Earth's equator. If a person stands at a point on the equator and look upwards, a satellite placed in a geostationary orbit will appear fixed at the same position in the sky all the time. In other words, the satellite always remains above the same point on Earth. On the other hand, a geosynchronous orbit may have a slight inclination with respect to the equatorial plane. Because of this inclination, the satellite does not remain exactly above the one fixed point on Earth. Instead, it moves slightly north and south relative to the equator. So let's shift to orbits classified by functionality. Let's shift to orbits classified by functionality. Polar orbit. A satellite in polar orbit travels in a north-south path, passing close to the Earth's pole. As Earth rotates, the satellite traces different stripes of the planet on each pass. That makes the polar orbits excellent for mapping, remote sensing, and global coverage over time. Next is Sun Synchronous Orbit or SSO. This is a special type of near polar orbit where the satellite passes over the same region at the same local solar time each day. Why is that valuable? Because lighting conditions stay consistent. So images taken today and images taken months later can be compared more reliably. That's why SSO is widely used for monitoring deforestation, sea level changes, and long-term environmental trends. The slide notes that SSO satellites typically orbit at about 600 to 800 km, moving at around 7.5 km per second. Finally, we have highly eccentric orbits, also abbreviated as HEO. Note this is a different meaning of HEO than high Earth orbit used earlier, so always check the context. A highly eccentric orbit is a very stretched ellipse with eccentricity close to 1 but still less than 1. Here the satellite speeds up at a perigee, the closest point to Earth, and slows down at apogee, the farthest point. A key benefit is the long dwell time near apogee. That means the satellite can hang over high latitude regions for longer durations, which is useful for communications in polar or high latitude areas. The slide mentions Molniya orbits as an application. And in nature, many comets, such as Halley comet, follow highly eccentric paths. To summarize, Leo is close to Earth, fast and ideal for imaging and human spaceflight. MEO supports navigation systems like GPS type constellations. GEO at 36,000 km appears stationary and is ideal for communication and weather. Polar and sun synchronous orbits are powerful for Earth's observation and consistent imaging. Highly eccentric orbits vary greatly in distance, giving long coverage times near apogee, useful for high latitudes. Thank you for watching.